Alright, we should be on 4.1 today. This is on page 295 in your textbook. So we're on page 295. We're going to be talking today about cubic functions. A couple things you need to know about a cubic function. First off, this is a function that is to the power of 3. Okay, we need to know that. That's very important. The reason we have a power of 3 is because we are taking x times x again. That's important to note. And it's also important to note because it tells us, that right there, tells us that there are 3 zeros. And hopefully you know by now that zeros means a couple of things. It means there are 3 solutions to a problem. It also means that there are 3 roots, and it also means that there are 3 x-intercepts. All of those are very important for cubic functions. So a lot of times these cubic functions will look something like this. They will have a xy ordered plane as you're used to, and the cubic function will cross through the x-intercepts, or the x-axis, up to 3 times. So it might look something like a roller coaster. 1, 2, 3, and it goes on forever. Here's my first x-intercept, my second x-intercept, my third x-intercept. And what happens here is we get 3 unique solutions. Okay, now this isn't the shape for all cubics. We're going to talk next period what happens if it's in vertex form. But this is exactly what happens as far as these graphs are concerned if we have 3 things multiplied, x times x times x, for example. Okay. Alright, then the next thing that you need to know are some of these definitions. Typically we're used to calling things maximums and minimums, but we have this new term called a relative maximum. And this right here, this point right there, is a relative maximum. And the reason it's called relative is because it's the highest point in this area, but obviously over here we can go even higher. So a relative maximum simply means it's the maximum within a specific area, kind of like a peak up here and a valley down here. We'll talk about that in a second. So the peaks are relative maximums. You can have multiple relative maximums in a graph depending on how the graph looks. In this case there's only one, but if this graph would have gone up again, back down again, then we would have had maybe a second relative maximum. Alright, so we would call this a relative maximum one more time because it is the maximum relative to these points over here, but not the maximum overall. Okay, this is actually what's called later on an absolute maximum. Alright, if we have a relative max, then we obviously have to have a relative min, and that's this point right there. That would be a relative minimum. And again, for the same reasons, this is the smallest in this area, but over here the graph actually gets much smaller. Alright, hopefully you remember how to do things like domain and range, because we're going to be doing that again, as always. The domain for this function is all real numbers, because I forever am going left this way. I'm forever going, that arrow, right this way. Our range is also all real numbers because I'm forever going down and forever going up. However, we're going to talk about things that are given in context, and sometimes we might eliminate some of these graphs. So keep that in mind as we go through, and we will be working on that. Alright, so go ahead and flip over to your page, and let's start looking at some scenarios. Alright, so now we are on page 296. And I want you to go ahead and read through this real quick and make sure you understand what's going on. And once you are done with that, go ahead and pause the video, and once you're done with that, let's come back. After reading it, you should have recognized that we are going to build these boxes from a square, flat, or rectangular flat piece of paper right now. Okay. Currently our paper is going to measure 12 inches, which is right here, by a total of 18 inches, which is right here. And we are going to be cutting from this paper the height. And that height is going to reference right here the height, here the height. So we're going to cut these little corners out, corner out, corner out, corner out. it's very important to recognize that all these heights are the same. And so what we're going to do is we're going to create this box, because as we cut this height out, we fold it up, and that might end up looking something like this. Here's my box. I've cut it out of the flat paper. This was one of the other classes. But as you can see here, these pieces have been folded up. That corner has been cut out. If I can get it here, that corner has been cut out. Once it's cut out, it's folded up. Okay, and it's also happened on the other side. All right, so we're going to create that box, and you don't actually have to do it, but you have to understand the process. Okay, so we're going to go through and we're going to create all these boxes, and we want to come up with a volume. And hopefully you recognize that volume is always, from middle school, length times width times height to make volume. And here's our three measurements. But height is going to be written first because depending on how much we cut will determine how much width or length we have. So for example, I'm going to do the first one here. If we have a height of 0, in other words we have not made any cuts just yet, then we should have a width. I'll call this my width. My width started at 12, so this will be my width of 12, and my length will be 18, which means in order to get volume, I must multiply 0 times 12 times 18 to make a total of 0 inches, and since it's volume, it will be cubed. And by the way, all of these are in terms of inches. Alright, so with your table, I want you to go ahead and fill out the rest of this all the way up to 7, and when you get to H, we're going to create an equation here for all of these. So go ahead and pause the video, make sure you fill that out, and then come on back once you're done. Alright, hopefully you have now finished that, and be sure to check all of these values up at my desk. I have all of the correct values up there, and hopefully you're getting all those accurately and completely as well. But we're going to now, most importantly, create this equation. This equation is going to be determined based off my height, because all of these values changed if the height changed. Again, if we were to cut deeper sections here, then my width and my length are both going to be reducing. Alright, so hopefully you recognize anytime you have an H value, I'm just going to call this H for height, then every single time up here, this width started at 12, and each time we reduced it by not one height, but 2 of these values. So this number should have gotten us a 10, I believe, and this number then should be 2 more than that would be 8, but from the beginning it was 12 minus 2 minus 2 again to get 8. So every single time we're subtracting 2 heights, and again the reason is because I have 12 inches this way, subtract that height, and subtract that height. So my generic formula becomes 12 minus 2 h's. Similarly, my length is a full 18 inches. For every height that I cut this way, I also cut the same height this way. So my formula would be a starting value of 18, and each new value is made by subtracting 2h. And the reason we write these is because now all I have is one variable, h, and the length and the width can be made if I only know h. And I don't have to have 3 individual variables this way. So all of these together will create my volume equation. My volume equation is going to be h times 12 minus 2h n times 18 minus 2h. And now what I can do is I can use that as an equation in my calculator. So what we're going to do is we're going to say x will equal our height. This is our height, this is our height, this is our height. And all of those will be x's in the calculator because we can't type in an h into the calculator. And that's very important because we can't also get a v in the calculator, so we're going to say y. Typically we write y equals, so y will equal our volume answers, because v for volume. So in this entire process, whenever we have an x value, we have to remember that's our height, right there. Our width and our length can be found if I only know my height by plugging into this little formula. That would be my width answer. My length answer would be this little formula. And obviously my answers that I get out all together, my y values in my graph, will be volume. So in other words, I would have an x, y ordered pair that would represent height and volume when I do these problems. So keep that in mind. Alright, go ahead and pause this video. See if you can answer all of problems 2, all of problem 3, and all of problem 4 now that we have that. So go ahead and do that, pause the video, come back when you are finished, check your answers, and then we will go on. Alright, so I want to make sure on number 4 that you understand what's going on. Right here it says, represent the function on a graphing calculator using the window and they give you this window right here. This is very important to understand what this window means. On the left side, this 10 and negative 10 to 15 is your domain, which means this is your x values. And on the right side, we're going to have our range, which is our, obviously, y values. So what they're telling us to do on this calculator here, they're telling us to type in the equation, so hopefully you have the equation already written. It's going to be the x, 18 minus 2x, and 12 minus 2x. And the order that you have them in doesn't really matter as long as you got them all. And then we're going to go over to window, and we're going to make our window match this value. These are the domain values. So this would be the smaller and the larger domain, which means our minimum is negative 10, our maximum is 15. We're going to go down to the y minimum of negative 400 and a y max of 400, and when you graph it, hopefully now you can see all the graph and all the important pieces of the graph. So using this graph, make sure you can answer all of 4. Okay? What's the maximum volume of the plant? Oh, let's go to this real quick and let's make sure we understand something. The maximum volume of the planter box. Now, if we have an actual planter box, okay, and this is our graph, I'm going to copy what my graph looks like. My graph looks something to this effect. I'll do it in blue here. It's going to look something like this and this and this again. Not exact, but a good shape. Okay, for our purposes, we cannot have a volume that's less than 0. So remember, this is our x-axis, which means height. This is our y-axis, which meant volume. So we can't have a y value of less than 0 because that would mean that our volume is negative, which we cannot we cannot really have in real life. We also can't have a height of a box being less than 0, which doesn't work either. So all of these values down here are thrown away. So all we get is this little part of the curve, and then we pick up over here as well. But if you think about it, once I start throwing these boxes out, these heights out, I can't have a height go on to infinity either. So all of this is also thrown out, because in reality I can't have an infinite height. I can have it on a graph, but I can't have it in reality. So the only part of the graph that I really even care about for our answered purposes are from here to here. And it kind of looks like a parabola. It's not, but it kind of does look like a parabola. So knowing this, we can basically ignore the bottom part here and this swoosh part there, and all we really care about is from 0 all the way up to whatever that maximum is, which you can figure out, all the way down to that 0, which looks like it's at 1, 2, 3, 4, 5, 6. So use those values and understand that. Okay? Come back and check all these answers again, and make sure that you are understanding how those values fit with our page. And then we are going to go on to the back. Once we understand that, we're going to do 5 through 8. Okay? Number 5, we are going to now put them in. I'm going to help you on number 5, and then you're going to do the remainder of them. So we now, on number 5, want to have a box with a specific volume. We want our volume to be 100 inches. Okay, now if you remember from before, volume equaled our y variable. So if I look at my graph, I want to be able to find when will my y variable equal 100. There's a nice easy trick here that we can do with our calculator. We know that this is the equation for all volumes based off of the height, the height, the height. Well, we can come in here and we can say, well, what if I want my volume, y, volume, to be 100? What I'm going to do is I'm going to graph both of these. And all of this line represents 100. So now what I can simply do is find out, where will that height exist? Where will that height be, or what will it be? And obviously we said earlier we can throw away this part of the graph, so I do not even need to worry about that equation. Hopefully you can remind yourselves how to calculate that intersection and that intersection. And we will have 2 answers here. So make sure you can do that, then answer all of part 5 and 6. You can answer both of those. Go ahead and pause the video, get those answers, and check those answers. Then we're going to talk about 7 and 8. Alright, hopefully you've checked those answers and made an understanding of what those were. On number 7, this is a little bit different, but they are telling us our base area on number 7. So I want to ask you a question. Hopefully you know this. How do we find area? Write that down, because that's important to know. Hopefully you said area is length times width. So in our equation originally, we had volume, and the volume equation was x, 18 minus 2x, and 12 minus 2x. So according to our problem, this area, which they're telling us is length and width multiplied, are these two answers. And that has to be an exact value of 12. So we can kind of erase all this just for this problem, not in reality, just for this problem, because they're telling us our base answer is 12. And we're going to rewrite our answer, or our equation I should say. Volume in this case is going to be x times 12, or you probably could just rewrite that as 12x. Okay? And so what we are going to basically do is come over and figure out how could I use that equation in my problem. So here's my equation. I'm going to use this and figure out my volume. So I'm going to come down here. I'm going to clear this one out because I don't need it anymore. This is my original equation, and I'm going to type in here 12x. And the reason I'm going to do that is because I want to figure out all the times when this and this together make 12. So they're kind of like a system now. And I'm going to once again graph my two equations. There we go. Now this one's kind of tricky. Again, remember that we don't have to worry about all these values, but I'm going to get a 12x intersection with my original graph right there. And that's going to create the answers that I need for my situation. So figure that one out and you'll be good to go. Last one, number 8, see if you can't do with your group. You want to make a 100 volume while the height is exactly 5. Is that possible? Yes or no? If it's not, tell me the answers that are possible. If it is, tell me the answer that is possible. And then come back and check your work, obviously. Once you are done with all of that, pick up a homework page at a normal place that the homework normally is. Make sure all your answers are shown. You will turn in 2 things to me on Google Classroom. You will turn in all of this, number 1 through number 8. All of those pages. I want to see that you're doing those. And you will turn in your homework as well. Alright, so I'm going to create 2 different assignments on Google Classroom. One is going to be the daily work to see that you have done that. The other is going to be your homework. Turn that in also. Alright, once you're done with all of those, you are free for the day. Make sure that you can help each other out. Make sure you keep my room clean. Appreciate you guys, and I'll see you next class period.